When you picture metal, you probably imagine a shiny, perfectly pure block of steel or gold. But in nature, almost none of that exists. The metals we rely on are trapped inside dull, heavy rocks, held in place by microscopic chemical bonds. Chemists call these specific metal-bearing rocks ores. Inside them, the metals are bonded to other elements, usually oxygen, sulfur, or carbon, forming oxides, sulfides, and carbonates. Reaching the metal requires winning a microscopic war. Even before the chemistry begins, it takes a massive physical effort, sprawling facilities and endless trains, just to gather the raw rocks from the earth. To win that microscopic war, chemists use a specific cheat sheet. This diagram represents the reactivity series. It's a ladder organizing elements from the least reactive at the bottom to the highly reactive at the top. The core rule of this ladder is simple. The higher a metal sits, the harder it fights to hold on to its chemical partners. Elements at the bottom have weak bonds that are easy to break. But as you move up, you encounter elements locked in bonds so strong they require extreme force to separate. We are going to climb this ladder from the bottom to the very top, scaling up the chemical force required to isolate the pure metal. We start at the bottom with unreactive metals like gold, silver, and mercury. Their chemical bonds are incredibly weak. Take cinnabar, a rocky ore containing mercury bonded to sulfur. This chemical equation shows what happens when we simply roast it in the air. The applied heat forces the sulfur out, replacing it with oxygen from the air to form mercuric oxide. Because the remaining bonds are still weak, we just keep heating it. That continued thermal energy completely severs the bond with oxygen, reducing the powder into pure liquid mercury. For these weak targets, simple heat is all the force required to achieve pure extraction. Moving to the middle of the ladder, we find moderately reactive nulls like zinc, iron, and lead. Simple heat fails here. We need a two-step chemical attack. If we look at these textbook equations, the first step is converting stubborn sulfides and carbonates into simpler oxides. We do this by strongly heating the ore, either in excess air, a process called roasting, or in limited air, known as calcination. Once we have a metal oxide, we move to the reduction phase. This animation shows what happens next. We introduce a chemical weapon, carbon. Carbon acts as a reducing agent, aggressively stripping away the oxygen atom and leaving behind pure metallic zinc. This two-step process is mandatory. You cannot easily strip a mid-tier metal until you force it into an oxide form vulnerable to carbon. But carbon isn't our only tool for the middle tier. Sometimes chemists use a stronger metal to violently kick out a weaker one. This is called a displacement reaction. It's highly exothermic, meaning it releases a massive, almost explosive amount of heat. You can see it in action here with the thermite reaction. By introducing highly reactive aluminum powder to iron oxide, the aluminum forcefully displaces the iron. The reaction generates so much thermal energy that it produces liquid iron on the spot, ready to weld a rail junction. Displacement turns the reactivity series into a weapon. By leveraging the strength of a higher metal, we can physically conquer a lower one right out in the field. Now we arrive at the top tier, highly reactive metals like sodium, magnesium, and aluminum. Their affinity for oxygen is so strong that throwing carbon at them does nothing. We have to bypass chemical agents entirely and instead rely on the brute force of raw electricity. This is known as electrolytic reduction. Look at this electrolytic cell. We melt down the ore, usually a chloride, into a liquid vat. When we apply a current, the negative electrode, the cathode, attracts the positively charged metal ions. Meanwhile, the positive anode pulls away the nonmetal ions. At the exact moment they touch the electrodes, an electron transfer occurs. As the equations on screen show, sodium ions gain an electron at the cathode to become pure metal, while chlorine ions lose electrons at the anode and bubble away as a gas. When chemical persuasion fails, directly ripping electrons away with an electrical current is the only way to shatter nature's strongest bonds. We started with simple heat for the weakest bonds, deployed carbon and displacement reactions for the stubborn middle tier, and used pure electrical current to break the unbreakable. These microscopic chemical battles are fought millions of times every single day. The towering blast furnaces and massive industrial plants you see here are designed entirely around executing these specific reactions at scale. This massive effort yields the materials that fuel our civilization: copper wiring for our homes, seamlessly welded rail lines, and lightweight aluminum aircraft frames. Mastering these invisible chemical forces allowed us to refine raw earth into the specialized materials that define the modern world.